On tap for today is a number of types of variations. First, we're going to start with direct variation, which is also known as a direct proportion. In this, we've got two variables, x and y, and they're varying directly. K ends up being a constant, so the equation we use is y equals kx. When we take a look at an inverse proportionality or an inverse variation, we have those variables being x, y equals k. Now, sometimes you'll see this variation written as y equals k over x. Doesn't really matter either way. All right. Now, the one thing I want you to note is that also, when you're given variation problems, typically they aren't necessarily asking for what the variation constant is. They'll give you two sets of circumstances. They'll say, if y varies directly with x, and y equals one term and x equals another, what will x be when y is equal to such and such? All right. In other words, you're going to be given two different cases for a variation. In that situation, we know that y over x is equal to k in this case. So y over x is equal to some constant. Typically, when we're given two circumstances, we can set up either a direct proportionality as seen below, where we have one y value over another y value is equal to the similar y value over the similar x value. In an inverse proportionality, first case, inversely related is equivalent to the second case, inversely related, because k is the same in each. K is the constant. It never changes. Another type of variation we're going to look at is a joint variation, which is simply a direct variation with a product of two quantities. So we say y varies jointly with x and w. So here is the direct variation. It's y equals k times something, okay? And that something is that product of x and w. And if we were given two situations, we could say in the first situation, because k is our constant term, we can say y over xw is equal to the second situation of y over xw, since k is equal to k. Let's take a look at a couple of problems and we'll show you what we're talking about. So in this case, it says y varies directly with the, or z varies directly with the cube of y. So if I were to write that, I would say z is equal to, since it's their direct variation, k y cubed. And now if you'll notice, they're asking me to find the constant of variation. So we're looking for the k value. So basically I have z over y cubed is equal to k. And now I just plug and chug. So I know z is 20, y is 1.5, and I'm going to take and cube that to find my k value. And I'll let you just plug that in and solve that for yourself. Moving to the next. So in this case, we have the period of a pendulum varies directly with the square root of the length of the pendulum. So again, I'm going to write a general equation for this. Period I'll call P, varies directly, so that's equal to k times something. All right, and this is the square root of the length. So the square root, I'll call this L. Now, it says if the pendulum length is 64 centimeters and the period is 1.6 seconds, what is the period of a pendulum 1 meter long? We need to notice right off the bat that we have a unit issue. We have centimeters here and meters here. So we're going to have to convert one or the other. It really doesn't matter. I'm going to convert the 1 meter. I know that 1 meter is equal to 100 centimeters. So I'll use that in my problem. So in this situation, once again, we have two pieces of information. We have the first piece of information saying, here's our length and our time. And in our second situation, they're asking for our time given our length. So in this case, what I want to do is I want to use my proportion that says P1 over the square root of L1 is equal to P2 over the square root of L2. And just start plugging numbers in. So length of the pendulum, 64. Square root of 64. The period is 1.6 seconds. I'm looking for the new period, so that's going to be P sub 2, and I'm given 100 centimeters. So in this case, P sub 2 is going to equal 10, because that's the square root of 100 times 1.6 over 8. And again, I'm going to let you solve that by yourself. The setup's the challenging part. Moving forward, now I have the volume of a sphere varies directly with the cube of its diameter. Keyword in this case, diameter, because we need to find out if they're going to give us a radius or a diameter. And in fact, they're giving us a diameter, so we can read this straight away. So it says the volume varies directly, so that's K, with the cube of the diameter, so D cubed. And again, they're asking for the variation constant in terms of pi. Okay, now volume of a sphere, all right, is given in cubics, so we're all good here. So 288 pi is equal to K times D cubed. Well, our diameter is 12, and we'll cube that. So K then is equal to 288 pi over 12 cubed. Once again, get that fraction, and you're going to be done. Next example. So now we jump to an inverse variation. So it says y varies inversely with the square root of x. We know our inverse variation. The way I like to do it is y root x equals k. And once again, in this case, we're given two situations. We're given our initial x and y values, and then we're asked to find a y given an x value. So I will once again set up two situations, one equaling the other. I'm looking for y sub 2 in this situation. So in my first case, I know x is root 12, and I know my y value is 40. In the second situation, I'm looking for y, and I'm given 15 for my x term. All right, now let's assume we wanted an exact value for this and no square roots. So I'll work through the entire problem this time. We have 40 root 12 over root 15 is equal to y. These will both reduce. 3 goes into both, so that's 40 root 4 over root 5 is equal to y. Root 4 is just 2, so that's 80 over root 5. And I'd have to rationalize. So I'll rationalize by root 5 over root 5, giving me 80 root 5 over 5. Whoops. Over 5. And 5 goes into 80, I believe, 16 times. So that's just 16 root 5 is equal to my new y value. All right. Well, let's move on. Once again, let's move on instead of going backwards. So in this case, I have the electrical resistance of a wire varying directly as its length and inversely as the square of the diameter. This is what we call a combined variation problem. We have a direct and an inverse going on at the same time. So I'm going to call R my resistance, and I'm going to set up a direct variation with the length. So that's K L. But I also have to have an inverse relationship going on at the same time with the diameter. So an inverse relationship with R would be a multiplication. So d squared R acts as my inverse, and that's going to equal K. And R, KL, acts as my direct, and that works with the length. So once again, we're given one situation and a second situation. So in this case, I know that K will equal d squared R over L. And I can set up now a proportion of these two situations. So once again, I'll just write this. D squared 1 R sub 1 over L sub 1 is equal to D squared 2 R2 over L2. So my first distance, or actually that's a diameter, is 6. So I'm going to take 6 and square it. I have a resistance also of 6 over a length of 6 millimeters of wire. My second situation, I have 90 meters of wire. And I just screwed this problem up. Let's go back. Sorry. I have 100 meters of wire. So that's my L. I have 6 as my diameter, and we're squaring that. And I have 6 as my resistance. Once again, sorry about that. Then we go back and we have 80 meters of wire. So that's our length. I'm looking for the diameter, d squared, and I have 15 ohms as my resistance. So now I'm going to isolate my diameter. In order to do that, I have 36 times 6. I'll multiply by 80 over 100. And I'll divide by that 15. And that's going to equal d squared. So if I take the square root of both sides, I end up with approximately 3.39 as my diameter. And that would be probably, what was that, millimeters? All right. Let's move on to our next example. So now we have a joint variation. H is going to vary jointly, so that's a direct variation, y equals k, times a product of these two terms, the squares of W and L. And once again, they want me to find the variation constant, so all we're doing in this case is isolating the k term and solving. And we can plug straight in. We have an H value of 36. We have a L value of 2, and we're going to square that, and a W value of 1/3. We're going to square that, and that will end up giving us our variation constant. Next, because the volume varies jointly as the height and the square of the radius of the base. So once again, volume varies jointly. That's a direct variation of a product of the height and the radius squared. And again, we're trying to find the constant of variation. So V over HR squared is equal to K. We take and plug in. We have a volume of 54. We have a height of 8 and a diameter of 9. Keep in mind, we're not looking for a diameter, we're looking for a radius. So what we have to do is take 4.5, which is the radius, square that, and end up with our K value. All right, let's keep moving. So that's it for the day. Here are your questions to answer, and we'll see you tomorrow.